Great. So welcome everyone to this week's Intercontinental Seminar on Gravity and Cosmology. This week we have the pleasure to have with us Ignacy Sawicki. Ignacy did his PhD in Chicago, and then after a few postdocs in New York, Heidelberg, and Geneva, he joined Prague, where he's still there. And today he's going to talk about causality and stability from acoustic geometry. So yeah, feel free to interrupt whenever you have questions.
Yes, thank you all for joining. Please feel free to just stop me and ask or tell me to move on, because I'm not sure exactly what the focus of the audience is. So if I'm not clear, just please stop me. So I will tell you about a paper that we published together with my student. This is the main chunk of his thesis, Georg Tränkle and Alex Wickman, one of my colleagues here in Prague. It's a sort of we asked a simple question. Probably we discovered a lot of machinery that's sort of half known, but maybe not completely. And in the end, I think sort of we've uncovered quite a lot of interesting structure, I think, which again, some of it is known, some of it is, I think, unclear to many people. So I will try to be very, let's say, pedagogical what I say. But the origin for me, at least, I'm a cosmologist, right? So the origin for me of this problem is of what we are looking at is the following, which is in cosmology, people look at often at something like scalar tensor theories, but just some sort of other new degrees of freedom propagating on a background, which the cosmological background, which violates spontaneously Lorentz invariance, right? There is a cosmological frame. So imagine, let's make things fixed. There's some, there's gravity, like the metric, and there's some scalar field. And there's some background solution, during inflation or during the late universe for dark energy, which is formed by this scalar field, which is moving in time. That's what it's allowed to do according to the FRW symmetries. And I would like to study what the fluctuations of the scalar are doing, right? So this is like small fluctuations around this background, and these are scalars, so they're sort of sound waves, right? So that maybe we could call them phonons in a relativistic medium. And the way you study them is when you write down some action for fluctuations. So of course there are also interaction terms which I'm throwing away, but this is at the quadratic level, you get something like this, and you cannot get anything more because of the symmetries of the background. So you get some kinetic term with an overall coefficient which could be dependent on time. You get some gradient terms with a coefficient which we call the sound speed, and in principle you get a mass. And then one of the things that is asked is, fine, so you've set up some background, you're trying to solve for, I don't know, let's say the phantom in the late universe that Deci may have discovered. You should ask whether your theory allows such solutions. So you should ask whether this is a stable configuration. So you compute this object on the background that you have, and then you compute from the action, you compute the Hamiltonian, and you check whether it's positive, right? Whether it's bounded from below. So in particular, you end up getting some momentum squared term. You end up with some gradient energy, and you have this mass in this way. And these coefficients you have over here, they appear in a particular way. And if there's any of these coefficients, they're all dependent only on the background configuration. If any of them are negative, then you're dealing with some instability of some sort. It could be benign, it could be a tachyon. That's we exploit in inflation, really, to generate perturbations in the early universe. So this is nothing to worry about, and I will ignore it from now on. But you could have a gradient instability or a ghost when these are negative. So you check the Hamiltonian is positive. And if it is, you're happy and you go away. So what have we done? Now let me do something a little bit, maybe not well motivated, but a bit insane, which is that I will take exactly the same action I had before, but I will make a coordinate transformation. I will boost in some direction, some spatial direction. And I will try to work out the Hamiltonian in these new coordinates. So this is clearly not the same object because Hamiltonian is not scalars. So I get something different. But in particular, I get both the kinetic term and the gradient terms are now corrected by things that may or may not be positive, depending on how fast this boost parameter is. So if I boost sufficiently fast, one of these could change sign, and then my new Hamiltonian is no longer bounded from below. So, like I said, this is not an observer independent object. This is not a scalar. So, well, okay, whatever. But so, is this a problem or is this not a problem? And if it is not a problem, wasn't important that at all that the Hamiltonian on my previous slide was positive? At some point I began to get worried a little bit. What is the meaning of all of this? And the justification that I always had in my head is that in the Hamiltonian I worked at previously, you go to sufficiently small enough scales, you're in flat space, it's isotropic, you're effectively in flat space, so you just appeal to the flat space solution, flat space discussion, and that's how you arrive at this positivity requirement. But surely there should be something just coordinate invariant, and this is how we ended up here, which is that whenever you have a theory which is derivatively coupled, it will break Lorentz invariance, and in principle not trivially, meaning that you will modify how waves propagate, how your solutions propagate, and these waves, these small fluctuations, they will propagate not in the space-time for a generic theory, but they will propagate in something else, which we call the acoustic space-time. Sometimes it's called the effective metric, but really it is really effectively a space-time, and just in the way that you can determine whether your solution in GR is sensible or not, the stability of this background can be determined from this acoustic metric in a way which is observer independent. And there are true instabilities, and those are related to the, and those would be the gradient instabilities and ghost instabilities, and those are related to the signature of this acoustic metric. But there are other things that look like instabilities, but are not, because they're related to choices of coordinates. And that's what I just showed you a moment ago. So let me make all of this concrete. So what we do is the following. We basically say, take any scalar tensor theory. So the only restriction we have at this stage really is that there's just no more than two derivatives. And you get some equation of motion for the scalar, whatever it is. I'm not providing a model at all. So basically what I'm discussing is true for scalars. But I think it's true much more generally, except you get this tensor structure with polarizations and so on, which you have to worry about, which complicates things. But the scalars are simple, so let's stay here. And then I'm no longer going to require that my background is symmetric in any way. So the background is something that is slowly varying. That's how I'm going to define it. So there's some phi bar, but it's a space-time configuration. It changes as a function of space-time. And there are fluctuations on top, and these fluctuations will be varying quickly compared to this background. So this is what's normally called the iconal ansatz, and it allows you to deal with situations where you don't have a particular symmetry for your background. And I will assume as an ansatz that my fluctuation is some amplitude, again, space-time dependent, and a fast oscillating phase. Okay, so S is my phase. And then I will plug in this ansatz here into my equation of motion. I will sort of go through the machinery of perturbating, collecting it order by order in this order parameter epsilon. And at leading order here, I will get an equation which looks like this, because there are two derivatives here. This equation will have a lowest order epsilon to -2, and will look this way. So there'll be some tensor tracing two derivatives acting on this phase, and this is called the characteristic equation of this differential equation equation system. And if you compare this with geometric optics, if you want, right, with Maxwell, you will see that it looks very much like having some momentum vector and a metric, and essentially defines the null. Some kind of null condition. So I will say here that since I started from the equation of motion, this is only up to normalization. If you have an action, you can do it. You can normalize the metric properly. And there's an assumption here. This is the only kind of real assumption that is important, which is that this principal symbol of this whole differential equation system, gravity plus scalar, is factorizable. So this is not always possible, and there are many theories in which it's not. So, but if it's factorizable, essentially there's a bit which looks like this. So I can define some degree of freedom for which there'll be at highest order the equation of motion will look like that. I mean, at lowest order in epsilon. Okay, and I want to say that this d mu s is really the canonical momentum of this fluctuation, and that this z is what I will call the, strictly speaking, inverse acoustic metric for the scalar fluctuations. Okay, and I would like to really treat it as a metric for the moment. So what does this really mean? So one thing you have to worry about is that now you have essentially two raising operations, and you always have to be very careful here, which is that normally your metric G mu nu associates vectors to covectors, and it's so transparent because of the beautiful notation that you don't even think about it. But if I raise and lower my indices on Z, which is just some arbitrary tensor that I've produced, which is not related, contains the metric, but in some complicated way, when I lower the indices with G, I do not get the inverse. So in fact, in addition to Z, there's really an inverse object to it, which I will define in this way, which I will call S because it's the upside down Z. And these two objects provide the metric and the inverse metric, acoustic metric, which allow you to connect covectors and vectors to different covectors to different vectors and vice versa than the metric does. You see, so there's a sort of separate structure of relating vectors and covectors, and from the perspective of G, they're completely unrelated. So I will always continue raising, lowering with the normal metric, and I will write these guys explicitly if I need to as different variables. Okay, so let's continue this analogy with geometric optics. So when I take electromagnetism in vacuum, I have what I already told you is this characteristic equation, but the meaning of this equation is that it relates the energy of the photon to its spatial momentum through some guy here, which is the velocity of light, speed of light. But there is a second equation, which you never think about, which looks like this, which is where I swap the position of the indices. And this one has a subtly different meaning, despite the fact it's basically the same thing, right? It's just the meaning of this is that there's some tangent vectors to some geodesic, these L's, and this describes where the photon is moving instantaneously, and therefore it actually traces out the geodesic eventually. But because of the fact that there's only one metric, and you never really think of these as a separate set of equations. However, the moment that you introduce this acoustic metric, and you're trying to sort of replicate this geometric optics picture, you end up with two distinct things. So you end up with a characteristic equation, which is now essentially an equation for the null vectors p mu of this scalar fluctations. And those give you a dispersion relation, which in principle can be some quadratic structure, which can be quite messy, where omega is I pick some observer, omega is the zero component essentially, right? So it's the energy of the phonon, and k is its spatial momentum, just as I had over here with light. And I also get a different surface. So this is really a different physical surface related to the null vectors of this S of this acoustic metric, where again this tells me these are rays now. So this tells me where the phonons are moving, and not about their energies. You see, so now this is a different null surface. But in the end, it is exactly the same equation, because all I have done is I've defined some n, which is z raising p, and I put the inverse metric here. So the equation is exactly the same, and therefore it must be the case that they are that somehow the information in the motion is also related to the dispersion relation. However, this relationship is non-trivial and it is frequently confused in many things people write. But this one will be related to causality, and this one will be related to energy positivity, if you want, right? So causality and stability will come out of this. One thing that you should bear in mind, and this is true apparently in all kind of in the geometric optics approximation always, is that the 4 vector along which things move is orthogonal to the momentum. And to me, this initially was completely shocking. So normally you don't see this because for something that is like for light, this is under null condition for light, right? This is just L mu up, L mu down is equal to 0. But this is true for any massless wave. Anyway, this is kind of so the point of what we're doing is we're trying to understand how this information about stability and things being well defined and so on is arranged in these 2 different surfaces. But let me make it concrete what these things are. So if you ever looked at something like a K-essence theory, so this is essentially the simplest example of something where the acoustic metric is non-trivial. So this is so X is my normal canonical term for a scalar, and this is an action, Lagrangian, which is some polynomial or some function of this canonical term. If I write and I do this iconal thing, I get this inverse metric Z mu nu, and it has this particular form. So it's related to the background gradients. So the background gradients are 0, this bit's not there, and then this is just G mu nu. But otherwise, this is a different vector this is a vector of some sort, and it provides a different metric. It's non-trivial. So if you take, of course, this d mu phi can be anything, but imagine it's time-like for a second. Then in some coordinates which are good for this, you have this acoustic metric is exactly what we have in cosmology, if you want, right? So there's some overall normalization. There is the CS squared term in front of what we the gradient terms, right? Imagine this is multiplying the derivatives of pi. And the inverse metric instead has the sound speed appearing here. But you now can imagine that if you go to different coordinates and so on, like you begin to end up in a situation where these things become highly non-trivial, despite the fact they represent actually just a nice, a wavefront which is expanding with some velocity CS. But okay, so let me actually draw what these null surfaces are on the assumption that they are actually cones, and I'll get back to that in a second, just to fix things. So what I've plotted here is the light cone is the purple cone here on the outside. There's some spatial surface in my coordinates. There's a time direction in my coordinates. And then for something which is moving less than the speed of light, I mean, it should be moving inside the light cone, essentially. So the cone is inside the light cone. However, which cone is it? It's this one. It's the one which is to do with the direction of propagation. So the S cone and the cone of the ray vectors, the ray cone, is time-like. And so this makes this is nice. No? This is how it should be, let's say. But if you look at the momenta, it is not. That guy is space-like. So so this is if you just literally plot the cone of the inverse to this metric S, it will be a space-like object outside of the light cone. And you can convince yourself that this must be the case. So I told you that P is momentum. So the 0 component is energy, and the spatial momentum is the spatial part. So this now is a surface of spatial momenta. This is the direction of energy, if you want. And energy is related in this way to momentum. It's multiplied by CS. So if CS is small, energy must be small, so the cone must be wide. So it must be this way. And therefore, momenta for subliminal things are space-like, while direction of motion is time-like. So we come back to this slightly insane orthogonality property that you always have between the two. And you only see this if you look at media. You never see this if you look in the vacuum. Okay? But okay, I've drawn these cones. I assume they exist, but is the surface even a cone? And the answer by analogy with G is basically either completely obvious to you, or you have to construct it. I have to construct it. But it's true that whenever this metric S and Z is Lorentzian, this is sufficient for the cone to exist. And there's some complication when you begin to look at it in detail, because these guys are sometimes not diagonalizable because of the non-trivial signature of the spacetime metric. But in the end, there is a property, which is that if you define this object with the mixed indices, so Z up, down, by multiplying with G, the determinant of this object is a scalar, and it is positive. If it is positive, then the system is hyperbolic, and your cone and your null surfaces are cones. Okay, but there are two hyperbolic choices. I mean, two Lorentzian choices, of course, and one of them is mostly plus, one of them is mostly minus. And in fact, we have convinced ourselves that this is the best way of defining in an observer-independent manner whether the degree of freedom is good or whether it is a ghost. So this is really signature. All observers agree on signatures and all coordinates. So both the hyperbolicity, or if you want, the existence of gradient instabilities, or the existence of ghosts are coordinate invariant statements if you go through this picture of the acoustic metric. So in particular, I just want to focus for a second on this ghosts, because people kind of say ghosts, they propagate into the past, or there are many kind of many things people say about ghosts, which are a little bit strange. So I just want to be very clear. So in particular, if you look at this equation, it does not care about the overall normalizations here. So the surface, the null surface, is exactly the same whether you have Z, which is overall good, or they put a minus in front of the whole acoustic metric, right? So the statement is that we're making as a sort of geometrical statement is that when you look at the fluctuations around some background, you care about the ones which are going into the future. So this is for the ray cone. It's the propagating. It's the vectors which are going out into the future. And the question and the acoustic metric maps these rays to the dispersion relation and the momenta. And good degrees of freedom have the momenta with positive energies, and ghosts have the degrees of freedom. Ghosts have the momenta associated with the lower half of the cone. Okay, and this is a geometry invariant statement. So that so you see, it's not the positivity or the negativity of energy that defines a ghost. It's really the half of the cone, and the cone, depending on your coordinates, may have some energies positive, some negative, or they all could be positive. And this will be, I will be more precise in a moment. Okay, but I told you, okay, find some tensor, I play around with this, I have null surfaces, great, but this is really a space-time. So to have space-time, you really need to have some sense of what happens when you move away from a point. And for that, you need a derivative. So we define the covariant derivative, but acoustic one of this bar, in the following way. We say, imagine there's a derivative with some connection, right, which is torsion-free, and it's compatible with this metric Z. So you will quickly convince, if you try to do this, you will quickly see that this connection, that is the acoustic connection, differs from the standard one by an expression that looks like this. This is completely fixed. I told you I haven't assumed the theory. This is purely just for any scalar field theory. This is true. There's such an object. Okay, so this looks like the Christoffel equation, but just with covariant derivatives. Now, the funny thing that happens is that the moment I require that the connection, that this derivative be compatible with Z, it is no longer compatible with the spacetime metric. So it's torsion-free, but there is this guy over here, this equation, and therefore this is a derivative, or it is a connection which has non-metricity inside it. You see, so the moment that you have this property that you have an acoustic metric which is not just conformally related to the usual spacetime one, you have non-metricity. Okay, and this is in fact, as far as I'm aware, the first time that. So normally people discuss this, but they usually do it in the following way. They say, look, I come up with there's a way of rederiving general relativity just using non-metricity but no curvature. And the moment that you try to introduce curvature and mix it with non-metricity, you actually end up generating a huge amount of degrees of freedom, and this program fails essentially. So you can have pure non-metricity gravity, it's like GR, it's exactly the same, or just pure curvature gravity or pure torsion gravity, and these three are exactly equivalent theories. Here's the first example of something which basically propagates exactly one extra degree of freedom, which is perfectly healthy, etc., because it's just a scalar tensor theory, but has both curvature and non-metricity. And this is interesting, but this non-metricity is super specific, and I will get to that in a second. So I have this derivative, and now I can write down an equation just starting from the from the iconal, from the fact that P is a derivative of a scalar essentially, and I can write down two equations like this. One tells me that these rays are null geodesics of this new spacetime, and that along these null geodesics, momentum is parallel transported. So in particular, this means that the standard way that you have some kind of killing vector, so somehow your metric doesn't depend on some particular coordinate, then that component of this momentum, i.e., for example, the energy, will be conserved. But the component of n is not conserved. So there's not similar sets of equations for P, for example, or with P and n swapped over here. So P mu defines really the conserved energy momentum, but it is not a geodesic itself. What is geodesic is n. Okay? And what n defines is the velocity of the modes. It defines transport, right? It defines how the modes move, and therefore it defines phase velocity of the modes for some observer. So let me just make a little segue into something called the Abraham-Minkowski controversy. So there's been for more than 100 years, there's been this question of how to properly define momentum, conserved momentum in media. So if you take a photon, imagine it's going at some energy E, momentum E, directly at a glass, a bit of glass where the refractive index is larger than 1, and if it's moving slower than the speed of light. So there's two ways of, if you believe that energy is conserved, right? There's two ways of defining what the momentum should be. One is that, and this is by Minkowski, that you're kind of inspired by the wave-like nature of this thing, and see that if the speed of light in glass is lower, then your wavelength decreases, and therefore your momentum increases. So clearly, your momentum should look like this. This momentum is space-like. However, Abraham said, no. I mean, that momentum should be time-like. So because it needs to move slower than light. So he defined momentum this way. So you can see where this is going. These two momenta, in fact, are orthogonal. And just by analogy, what I've been describing to you, this Minkowski momentum is the canonical momentum that I've been discussing. It's this dμs that I've been discussing. And this is the one that these arguments about the killing vectors and so on tell you. These are the guys, this is the momentum that's conserved. This is the energy that's conserved, this is the momentum that's conserved. If you have killing vectors. Now, the Abraham momentum is proportional to the ray, but I was strictly speaking proportional. So in fact, the proportionality is through Z, and this one is not conserved in general. So essentially, this approach makes clear really how you should what resolves this problem here. That's been that's sort of resolved in ways which are depending so people discuss in very complicated ways how to resolve this, and I think this is kind of clear from this perspective. Okay, now here is something that we I think is very interesting. And essentially determines a lot of the properties of this. So I told you that there's this non-metricity, and then so in general this is some tensor of some particular symmetry structure, and it has 40 degrees of freedom, I think, if I remember right. So, however, in our case, it is not like that. So in our case, when you trace this tensor, so you produce something called the Weyl vector. You find that it is always given by a derivative of a scalar, and in particular, the scalar is the determinant of the acoustic metric. So it's some volume normalization of the acoustic metric. And this is super important because it allows you to relate divergences in the acoustic space-time with divergences in normal space-time. So just through this equation, you essentially end up getting this. So whenever there's something which is conserved in the acoustic space-time, so divergence of J is 0, some vector, some current, there is also it is also conserved, or rescaled version of this is conserved in the normal space-time. So you don't create new conserved charges; they are conserved in both the metrics. See, and for example, one of such charge is actually the flux. So at one level down in iconal, you get an equation which is just the flux conservation equation. It tells you that the amplitude, this A that we had in front of the definition of, as the coefficient in pi, in the fluctuation pi, the amplitude squared is conserved along a bundle of geodesics. So this is normally what you use to calculate luminosity distance or angular diameter distance and so on. But this is now general. But this implies that there's also some conserved charge in space-time, which has this particular form. And it's conserved along these same geodesics and mu, which are no longer geodesics of space-time, they're acoustic geodesics. So there is you can essentially you can relate these two, and in particular the Hamiltonian will be such a charge. I will get there eventually. Okay, so let me give you some examples of now we have this covariant structure giving you dispersion relations and so on. I can begin to actually try to understand what happens when I go to bad coordinates, when I change my coordinates. So when you have a light cone, it is invariant with respect to Lorentz boosts. However, when I have something which is inside the light cone or outside it, if I take a normal Lorentz transformation, they change, right? They're not null surfaces. So in particular, if I have some degree of freedom which is moving slower than the speed of light, and therefore it's raised inside the light cone, I can boost myself to a velocity which is faster than the velocity of these guys. And when I do this, what happens is that my modes will no longer propagate in all directions. So in the isotropic frame, when I'm sitting at rest with respect to medium, the waves are going out, the sound waves are going out in all directions symmetrically. But when I'm in this boosted frame, they're all moving toward in a particular direction in space, in principle, if I boost fast enough. So what happens is that I form a geometrical structure called the Mach cone, which for photons would be the Cherenkov cone, which delineates the sort of outside of where the fluctuations can go. In particular, it's the projection onto my spatial surface of this 4-velocity cone. Now, the moment that I am moving supersonically, so I have this cone that forms, there is a sound horizon. At the same time, I end up getting, from my transformed dispersion relation, I end up getting a situation which have negative energies. So in fact, the Mach cone is produced by the surface which has 0 energy in the rest frame of the observer of this cone. And inside the cone, there are some modes which are the ones propagating against their momentum, essentially, which have negative energy. Okay, and if I look at this metric S, the sign of the 0, component flips the moment that I go from subsonic to supersonic. So if you were to be using this as your metric to determine whether you have ghosts or not, for example, you would misidentify them because you would think that the 0 component has the wrong sign, I have ghosts or something like that. And this is not that. This flipping purely determines whether you have supersonic motion, or whether you use an observer and moving supersonically with respect to this. Now, this is purely a coordinate discussion. So clearly there's no physics that happens. I have negative energy modes. There's no interesting physics unless something interacts with these sound modes And then, so if I have some particle which is moving supersonically through the medium and interacts with this medium, then it can extract energy from this medium by producing these negative energy modes from the point of view of its rest frame. And this is exactly what Cherenkov radiation is. So essentially, we have uncovered how in this covariant setup to find what Cherenkov radiation looks like. So it's a kind of, it's in principle a real instability when you're moving supersonically through a medium. And now let me sort of make something about the geometry of this a bit more precise. So I said, imagine that you have some kind of duck which is moving, supersonically, it's flying supersonically through the air, right? So there's a rest frame of the duck and there's a rest frame of the medium of the air. And the rest frame of the duck is not moving. But there is a sound horizon because the fluid essentially, the modes are all moving to one direction because from its point of view, the medium is moving. And therefore there is a surface, a conical surface, which is delineated by the energy from the point of view of the duck being zero. And on this surface, it's defined by, so zero energy. Remember I told you that this relation is always true. So the momentum of these modes and the direction in which they move, the spatial one must be orthogonal because the energy is zero component is zero. So from the point of view of the duck, what is happening is that momentum, so modes which have spatial momentum pointing this direction orthogonally to the surface of the cone, are being produced by the duck, and then they move along the geodesic equation, right? They're being parallel transported by n along the cone. But if you do the boost to the rest frame of the medium, you find that this was exactly such a setup that in the new cone, which has a slightly different opening angle once you boost because of aberration, the momentum and the direction in which the rays are moving, in which the modes are moving is actually parallel. So if you purely look in the rest frame of the medium, you never see this funny behavior, and you don't even differentiate between these two. So and the reason I say all this is exactly that our approach has allowed us to describe media not in their rest frames, which is not the usual approach taken. And in fact, there are in some theories, you can construct acoustic metrics where you cannot even boost yourself to the rest frame of these mediums. So this is a way of essentially understanding that properly. Okay, so let me move on to the other dual case. So now I will actually do the thing that some of you may not like, which is I will now allow my modes to move superluminally. So the speed of the phase velocity will be superluminal. And then I will boost again, like I did previously, in such a way, so fast enough, such that from my point of view as an observer, in fact, the motion of the modes will be into the past. So outgoing things will seem to be ingoing. And there's, in fact, a lot of confusion here because people, when they, in such weird coordinates, they try to, construct the retarded Green's function, and they will frequently take the things moving to the future. So they will take this half of the past cone and this half of the future cone. But this is not the correct thing to do. For the correct Lorentz transformation of this Green's function, you must take basically all the modes belonging to the top half, even if they're going into the past. So immediately you know that this is somehow sick, right? You need to know that since things are going into your coordinate past, these are not good coordinates, right? In particular, the spatial surface is not a good Cauchy surface. So what does this appear like from the point of view of the dispersion relation? Well, from the point of view of dispersion relation, you have the momentum cone is now time-like. It is narrow, and exactly the moment where modes go into the past is the same moment when this momentum cone no longer covers the whole of the spatial hypersurface. This means that some modes just disappear they don't propagate. There are some momenta which are not covered by this cone. They don't propagate. So if you naively assume that all the modes propagate, you will find there are some energies omega which are complex. And therefore you will interpret that as having ghosts. So you see, it might happen that if you boost in a supernormal situation, if you boost fast enough, your acoustic metric will change sign, and you will interpret your degree of freedom as being a ghost when it is not. Or vice versa, you will interpret a ghost as being a good degree of freedom because that 0, 0 change sign. This is again a coordinate effect. I mean, at the end of the day, it must be true that if I solve the physics to some sensible coordinates where the Cauchy surface is good and my spatial surface is, I'm free to define initial conditions there, everything will be fine. And if I transform that solution to my new coordinates, it should be the correct solution. The problem is that because this is not a Cauchy surface, you can't really solve the problem in the bad coordinates. So you should never do this. Okay, let me move on. Skipping this. So there's one more aspect of this sort of standard construction in general relativity, which is that you can also ask about something called the energy momentum tensor, right? So imagine again, I now have some action for my fluctuations. Again, this is just the free part. This is the metric normalized properly. So it just looks like it would do if you had the normal space-time metric here, right? Root minus g and so on. So if I do it this way, then I find the following. The scalar equation of motion, in this case, is just box pi, except it's the acoustic box. But essentially, the scalar waves propagate according to the Klein-Gordon equation, but of this funny space-time. And there's an acoustic energy momentum tensor, which I get by varying with respect to z, which looks like the canonical scalar energy momentum tensor, with some, but with not the normal space-time, but the acoustic space-time appearing here. And this object is conserved, just like the normal energy momentum tensor would be, but in the acoustic manner, right, with an acoustic derivative here, but it is conserved. But it is not at all related to any sort of perturbation of the normal energy momentum tensor. So this is a really funny object, in that it's not that this is perturbed energy carried by the fluctuations that you would define using the space-time energy momentum tensor. It is a completely different object, and yet it is conserved in some way. And in particular, what you call the Hamiltonian density for fluctuations is the 0, 0 component of this object, right? You form the Hamiltonian out of this, in fact. So it's good that it's conserved, but is this really to do with energy? You know, kind of say, is this really is this quantity relevant in some way? The answer, thankfully, is yes, but it is not the normal space-time energy. It is acoustic energy. It is some generalized form of energy. Now, so like I said, so what you call the Hamiltonian in the high frequency limit, right? So going to this iconal limit, it contains the amplitude squared, and then contains both the 0 components of the momentum, so the energy of the modes, and this thing that appeared as the 0 component of the ray, what we call the Abraham energy, but which itself is not exactly an energy, right? It's a different. It's the 0 component of this ray, and in particular, sorry, I should have said this, that this object, which is T with the mixed signature, so T multiplied by Z averaged on this iconal limit, really has this super clear meaning. It's like the modes P parallel transported along N, and you count the number of them as amplitude squared. And thence the energy is related to the 0 components of P and N here. Now, this guy is conserved. Introduce a killing vector so that there's something like a conserved energy in the first place, right? So you form some object just like in the standard case. But if this is conserved, when you have a killing vector, by the arguments we had before, by this funny property of this non-metricity, it's also true there's some current which is conserved in the normal space-time, and there's a charge which is conserved in the normal space-time. And what is this charge? In this case, the Hamiltonian. So somehow we've gone around this, we've gone around in some complicated discussion. We've rediscovered that the Hamiltonian for fluctuations is a conserved quantity when your acoustic metric does not depend on time, which is the only situation in which there's such a thing as a conserved energy. But it's conserved really in the normal space-time sense. but completely non-trivial, as you can see. So let me kind of begin to wrap up here. So this is the iconal version of things, right? So this is for the high frequency version of things. But let me try to write down the full Hamiltonian. Is this somehow related at all to these cones that we've been discussing? So the full Hamiltonian for fluctuations requires me to set up some foliation. So this is no longer a local issue, right? I need to set up some foliation, and on my slice, I can write down my fields and write down the Hamiltonian density, and then integrate that to get the Hamiltonian. So if you start with here, you can, by playing around with this, the Hamiltonian that you get looks on some arbitrary foliation, right? Looks like this. There is a bit which looks kind of like gradient energy and kinetic energy. This is canonical momentum, remember? With coefficients that on a good Cauchy surface. So remember, this is the situation in which there's no propagation of modes into the past. This is positive definite. And Z2 is defined as a kind of square of the matrix. I didn't have time to go through this, but Z2 is related to some quadratic structure formed with the acoustic metric. So if you're familiar with something called the radar metric, it's very similar to this structure. So this part of the Hamiltonian, essentially on a good Cauchy surface for a problem which is hyperbolic, is always bounded. Okay, and depending on the sign of sigma, which is whether it's a ghost or not, it's bounded from below or above. But then there's a second part of the Hamiltonian, which is linear in momentum and in the field, so may or may not be bounded. So we have proven that it is bounded, but only if you are subsonic with respect to the fluctuations. If the observer of the foliation, the co-moving observer of the foliation is subsonic with respect to fluctuations. Otherwise, it's not bounded. So this is exactly the situation which, when you're moving supersonically, there is now really negative energy. Hamiltonian is unbounded. Then you produce Cherenkov. You're free to produce Cherenkov modes by extracting, by stimulating the medium. And if you're subsonic, you are not. But you see, it's like these are the only two properties which determine whether the Hamiltonian is positive or not. Is it a ghost? Is it a Lorentzian metric? Are you subsonic? And that's it. If these three are satisfied, the Hamiltonian is always bounded from below. Okay, but that sounds like Cherenkov radiation, which means this is unbounded, should be bad. I mean, it is really an instability. You do lose energy, right? So you produce these modes for free, apparently. So is it really actually catastrophic somehow in this picture, or is there something that saves you? And the answer is yes, there is something that saves you. It's kind of interesting. So, so here the Hamiltonian. So imagine that I have now coordinates where I'm supersonic with respect to the medium, right? So now Hamiltonian is for some. The Hamiltonian for some modes is negative. The Hamiltonian is not bounded anymore, right? So, however, if you take a killing vector psi, there is an associated charge. As we can form out in the same way as I was discussing before. We can form out of this acoustic energy momentum tensor, and it looks like this: it's the integral of psi, my frame, and this energy momentum tensor. And when I rewrite it, I get some complicated expression, but it's in the end some tensor, not the acoustic metric, it's some other object completely, tracing this derivatives here. And we have proven, and this is actually super non-trivial, this is not a simple proof, but we have proven that this Q is positive definite, this Q mu nu is positive definite, and therefore this charge is positive, if and only if your acoustic killing vector is time-like, but not with respect to the normal space-time metric, but with respect to the S metric, to the acoustic metric. S and not Z, by the way, this is important. And in particular, it's positive for non-ghosts and negative for ghosts. So the answer why Cherenkov is not catastrophic is that, yes, the Hamiltonian's unbounded from below, but there is some other charge which is carried by the medium, which is transferred to the particle going through it supersonically. And once all that charge is essentially depleted, the process stops. And it stops when the particle is no longer supersonic. So this is like the particle extracts energy, it becomes accelerated. It's a little bit confusing as to which way it gets accelerated, but it slows down, in fact, with respect to the medium, and then this charge is depleted exactly when the particle is moving at the speed of sound. And this is so this process arrests. But if there were not such a common time-like vector between the acoustic metric and the normal one, then this process would not stop. Okay, so we've basically concluded that both for the Hamiltonian, it's a non-local thing on the foliation. It is not just the high energy modes. It is any configuration at all of this massless problem. And the geometrical picture are basically the same. And they tell you that these configurations, which of course you might have said, of course, they're pathological, but these configurations of the cones are bad, and the other configurations appear okay. So one bad configuration is when the light cone here in green overlaps with both the future and the past of the other degree of freedom, so the top and the bottom half of the ray cone. So this is bad because this is truly acausal. So before we had acausality on the bad Cauchy surface, but there was still causal ordering you can prove. But here there's no causal ordering anymore. So this is really a time machine, if you want, at the point. And this is also problematic because there isn't a bounded charge which would stop. So you see, both of these guys are supersonic with respect to each other. So they will spontaneously produce, any mode of one will produce Cherenkov radiation into the other. This never stops because there is no charge at all that is bounded. And of course, you might have said, yes, but I mean, this clearly a pathological. I mean, who discusses cones pointing along the x direction? But now imagine this case, which I think is really quite physical, which is you have a light cone, you have two fluids or two gases of some sort, whatever, which are moving past each other faster than the speed of their own speeds of sound, but both subluminal. There's no superluminality here whatsoever. But they're moving faster than the speed of sound, and they have no bounded charge. And therefore, this is a completely unstable configuration, which will be destroyed over some time scale related to the interaction cross-section. So imagine you have dark matter smashing into whatever normal gas. There is some, but supersonically, there is such a process that happens there. So this is basically what I had to say. So the takeaway really is that the right way to think about these kind of non-canonical systems of equations of motion, like things that are derivative interactions, let's say, is that their fluctuations propagate not in the usual space-time, but in some acoustic space-time. And the properties of acoustic space-time determine all the relevant things for stability and conservation of energy and momentum and so on. Real pathologies are invariant for all observers, as they should be, and those are related to the fact that, for example, your equation of motion is not hyperbolic, which you call a gradient instability when you sort of do it when you do it in cosmology, for example, or that there are ghosts, and this is related to the wrong choice of signature of a Lorentzian metric. But then there are also bad coordinates, right? And bad coordinates give you things that, if you're not careful, you can interpret as being either healthy or, in fact, unhealthy. So one thing that you can find is that if you have coordinates which where your slice is not spatial with respect to the momentum cone, then you will see that there are some. Then things will look like ghosts, or vice versa. Ghosts look like good degrees of freedom, but these if you try to actually write down any process which might involve them, you'll find that nothing happens. And the reason for that is these modes don't actually propagate. They're not in the cone at all. Supersonic motion, we know happens. We observe Cherenkov and Mach cones. We know this is there. So we have basically created constructed a covariant description of that process. And we see that in this covariant description, what you call the energy of a mode really becomes negative when there's a sound horizon. And the Hamiltonian is unbounded from below. And this is the correct thing. But if you don't have some pathological situation with the cones not overlapping, so there's at least one common vector inside both the cones, you will, in the end, have some charge which is always positive and will bound the motion, and therefore the instability will stop. But these, in principle, both of these, in principle, are physical instabilities. If these coordinates are associated to some real degree of freedom, as opposed to just coordinates that you've written that don't have a physical meaning. And the Hamiltonian picture is really equivalent to this geometrical picture of the cones. It really is exactly the same, right? So we've managed to recover exactly the same conditions for the stability from the Hamiltonian picture. The Hamiltonian, if you have a time-like killing vector, is a conserved charge, but both in this acoustic space-time and in normal space-time. And what this means is that if you're trying to be kind of a little bit maybe sort of more democratic in the way you think about this, is that really for any background of any number of degrees of freedom, on the assumption of this factorizability, of course, that I made initially, all the metrics, in fact, the space-time metric, the acoustic metric, and so on, that they're all actually, they are all they are all on the same level. The space-time metric or the space-time energy is not in any way more fundamental for that background than any of the energies of the fluctuations here. And what you need to, when you have gravitational degrees of freedom, which you always do when you have gravity, right? You need to there is a sort of time-like and space-like vector with respect to normal space-time metric. But the reason is it's relevant for anything is exactly because you have degrees of freedom associated for which this metric G mu nu is the acoustic metric, if you want. If there were no such degree of freedom, you switch gravity off, etc. It doesn't matter if G mu nu, there are time-like, if things are time-like or space-like with respect to G mu nu. So you can solve things in coordinates which are bad with respect to normal space-time metric if you want, if you don't have gravity. So I think this would be it. Yeah. Thank you.
Thank you very much, Ignacy, for the very nice talk. Are there any questions from the audience? If not, let me start. Let me see if I got this clearly. So you have this non-metricity of the acoustic connection, and then
Yes.
this has a special, let's say, property which ensures somehow that any current that might be formed from this energy momentum tensor, from the acoustic energy momentum tensor and a killing vector field, will be somehow conserved in both spacetimes.
Yes, you see, I haven't picked a theory. So I haven't picked a theory. It's really just by construction. This is called the disformation tensor normally.
Yeah.
This difference between the connections is exactly this expression. And that's it. And the fact that it has this expression means immediately that when I take so this formation tensor is related in some slightly non-trivial way to this Q. But if I take the trace of this Q, I exactly can show that it must be the case that the Q is a derivative of a scalar. So this is just always true. And then the moment this happens, so this is this expression here. And this is enough to then, you just play around with your normal, so there's divergence of some vector, with a covariant derivative. You can rewrite it as a, partial derivative with G in the root G in the appropriate places, right? There's nothing funny. I'm not doing anything funny, right? So you can you can just do this, and because of this particular property, you can essentially exchange the one derivative for the acoustic derivative for the spacetime one, and you end up with this statement, right? That there's essentially, for any conserved any vector conserved here is automatically conserved in spacetime up to some normalization factor.
Mm-hmm.
So there's a kind of interesting question of like, okay, there's some amplitude here of fluctuations moving along some geodesics in this acoustic spacetime. What exactly is this that's conserved in normal spacetime? And so the best I can tell is that it's somehow related to the shift charge carried by these fluctuations. So because there is no mass, there's a shift symmetry for the fluctuations, right?
I see.
And then the space-time conserved object is related to the shift charge carried by these fluctuations, and this gives you a conserved flux on the acoustic space-time. But it's a little bit still unclear to me exactly how this works and how general this is. But for k-essence, I've proven this is true at least.
And is this true? Do you think that, this structure, this double, let's say, conservation, is somehow special to like scalar perturbations, or could this arise in perturbations for other fields?
Yeah, so I think the complication becomes that once you have, let's say, imagine you can try to do this for photons, no? So for vectors. So you have this problem that you essentially have 2 degrees. There are 2 degrees of freedom there now, and there's some determinant that multiplies 2 acoustic metrics together, and then you have to. So the thing gets a little bit more complicated when there's no birefringence. It just factorizes into 2 such acoustic metrics, and everything goes through.
Mm-hmm.
The situation with birefringence, I'm not. I don't know. Sort of how. So it's not clear what but my feeling is essentially is that what we've done for scalars essentially uncovers the same physics that would occur for other fields, at least in some limits. Except that for the other fields, it's a little bit more complicated because you have there's more index structure, right? And then you lose the simplicity of it, let's say. But I don't see why it would be different.
Mm-hmm.
So there are like various things that make sense, how you define properly phase velocity and the refractive index, and all these things are super general and nothing to do with the vector nature of light. It's just exactly the same thing appears here.
Mm-hmm. Nice. Any other questions? I might have another one. So this Cherenkov emission that you get. So in curved spacetimes, or I don't know, in any non-trivial, let's say, scalar background, is there like a covariant criterion to ensure that this back reaction from the emission will not destabilize the background geometry?
Yeah. So let's say the covariant statement is really something like this. When you have multiple degrees of freedom, there are cones at all points on your background. So if your background space, it has to be. So this is now, this is a picture at a point, right? In principle, these cones, of course, they move around as you go between different places on your background, right? But there must be a common time-like vector, i.e., inside both of the ray cones, for there to exist this current, which this charge is bounded, this cubic side that I defined. So if that exists, then you will eventually, there's only so much energy you can extract from the medium. However, if this, in the case like this, there is no such charge, and I think what will happen is that you will continue to extract energy. So if you have a mode, it will just be able to produce more modes of the other. The criterion for Cherenkov, the geometrical criterion for Cherenkov is that for any particular mode, which is some ray here, the sound cone lies outside of it.
Yeah.
So you always get some Cherenkov whenever you have a degree of freedom which does not have the same speed as some other degree of freedom. But the question is whether this can happen spontaneously, or whether this can happen only if you have a source. Maybe this is another way of approaching this problem. So in situations where you have common time-like vectors, it only happens when you have a source. So you have to have a superluminal mode. I mean, you have to have a supersonic mode of 1 degree of freedom, and that can produce Cherenkov radiation essentially. If you are in this setup where the two cones don't overlap, you can produce Cherenkov from nothing, in fact. So this just the vacuum will destabilize. So this is really what time scale this happens and so on is like, I don't know. We've not computed that yet. But I think such a background is just unstable even when you start with no fluctuations.
I see. Good. Yeah. Are there any other questions? Let me stop the recording then.